Logical systems operate within closed parameters. They start with defined rules, known conditions, and a delimited problem. Because the environment is perfectly bounded, the system executes solutions with absolute precision. Intelligence, however, operates in open reality. The environment is incomplete and too complex to grasp entirely at once. Solving problems here requires the system to advance partially, building hypotheses and correcting itself during the process. Because it cannot see the whole picture from the start, deviation is a constant part of the path. We can describe this as interpretive drift. When an adaptive system processes novel, complex data, its initial patterns may pull it away from the goal. Without a stabilizing force, these small initial errors branch into diverging paths, making the trajectory unstable. This drift isn't a sign of a defect. It is the operational reality of any system that must adapt to an environment it does not yet fully understand. Classical information theory generally views redundancy as a mechanism for error correction. It's a way to ensure that if a message is transmitted over a noisy channel, it can be reconstructed even if some parts are lost. But in an open, intelligent system, recovering lost data is only half the battle. Simply receiving a message doesn't tell the system how to interpret what that message actually means. Redundancy serves a more active function. It acts as a corrective force that intervenes while an interpretation is still forming, providing the extra signals needed to keep the system's trajectory aligned with the intended meaning. Redundancy is more than a safety net for noisy channels. It is the tool that allows an intelligent system to maintain its orientation within a complex environment. In language, a plural pronoun acts as a first constraint, narrowing possible interpretations. As redundant markers arrive, like a plural noun or verb, each acts as an intersecting filter. These overlapping signals force the system to converge on a single meaning, preventing interpretive drift. This principle is essential for system architectures like the Aurora project, which rely on cascading events to process information. In these systems, a change in one node triggers a cascade of transformations across others. As this chain grows longer, there is a risk that the original constraints will weaken or become lost in the complexity of the propagation. Redundancy ensures that critical constraints reappear at different stages of the cascade. By reinforcing these signals, the system ensures that local changes do not derail the global objective. Consider a novice system with randomized internal patterns. To reach a goal, it relies on heavy external redundancy, like constant examples, to force a specific pathway through its unorganized matrix. When this external guidance successfully leads the system to the objective, the system identifies the most effective patterns. It reorders its internal weights, creating a stable hierarchy where the paths with the least deviation are most accessible. Once specialized, the system requires fewer external signals to perform. A single cue can now activate a complex internal structure that previously required 10 examples to trigger. Specialization is the process of turning external, redundant guidance into permanent internal structural efficiency. Large language models attempt to simulate this specialization through context. When a user provides a long, detailed prompt, they are using redundancy to guide the model toward a specific domain. This context forces the model to temporarily reorganize its activations. A specific cluster of pathways illuminates, acting as a specialized expert. Because deep weights are frozen, once the context clears, the glowing cluster fades, returning the model to its general state. This creates a bottleneck in centralized architectures. They cannot easily consolidate what they've learned during an interaction, meaning the user must provide the same redundant guidance every time they start a new session. True specialization is local. A system optimized to solve problems in biology uses a specific order of patterns that would likely cause errors in architecture or law. An alternative approach moves away from a single monolith toward a network of specialized nodes. These nodes might share a common language, but each one maintains its own permanently optimized internal hierarchy for a specific field. In this model, the role of the system is to route queries to the specific node that already possesses the most efficient pattern hierarchy for the task. This design allows a system to retain its expertise as a structural feature. It no longer needs to rely on massive external prompts to find its orientation, because that orientation is already built into the node's internal weights. In this architecture, intelligence is defined less by the volume of data a model can access, and more by how its internal patterns are organized to solve a specific problem. Redundancy provides the initial map, but specialization allows the system to hold its ground.